What if everything we thought we knew about the universe was built on incomplete information? Picture a star so ancient it witnessed the first flickers of light after the cosmic dawn, a silent observer that has been shining for over 13 billion years. These aren't just distant points of light, they are time capsules, preserving secrets from an era when the universe was in its infancy. Each of these ancient star systems tells a story that defies our textbooks and challenges the very models we use to explain reality. They push the boundaries of what we believe is possible, revealing gaps in our understanding of cosmic evolution, star formation, and the origins of everything around us. In this video, we're setting out on a journey to explore 25 of the most mysterious and groundbreaking ancient star systems ever discovered. These celestial anomalies are more than just old, they're revolutionary. Some contain stars that, according to all known physics, shouldn't even exist. Others are entire galaxies that formed too early, too fast, or in ways that leave astronomers speechless. Each one is a piece of a grand cosmic puzzle, helping us reassemble the story of where we came from and how the universe took shape. From the outer halo of our own Milky Way to the faint, forgotten dwarfs orbiting at the edge of visibility, these systems are rewriting astronomy as we speak. You're about to see how discoveries like these are shaking the foundations of cosmology, forcing us to reconsider ideas as fundamental as dark matter, the Big Bang, and the life cycle of stars. This isn't just about science, it's about reimagining our place in the cosmos. So settle in, open your mind, and get ready to see the night sky in a whole new light. By the end of this journey, you won't just understand what makes these star systems special, you'll feel the awe that comes from peering deep into time itself. But why should we care about these ancient stars in the first place? What makes them so much more than just old points of light? The answer lies in the stories they tell. Think of the universe as a vast, ongoing crime scene, and astronomers are the detectives. The present-day cosmos is messy. It's been changed and rearranged by billions of years of stellar explosions, galaxy collisions, and cosmic evolution. The evidence has been trampled on, so to speak, but these ancient stars, they are the pristine, untouched witnesses to the very first moments after the Big Bang. They are our only direct link to the cosmic dawn, holding within their light the chemical fingerprints of the universe's infancy. To date these stellar fossils, astronomers act like cosmic chemists. The primary tool is spectroscopy, spreading a star's light out into a rainbow of colors and looking for specific, dark lines that act like a barcode. Each element absorbs light at a unique wavelength, creating a telltale line in that barcode. The key clue is metallicity, which in astronomy means anything heavier than hydrogen and helium. The early universe was a soup of just these two light elements. All the iron in your blood, the calcium in your bones, the oxygen you breathe, every heavy element was forged in the nuclear furnaces of stars, and then scattered across space when those stars died in spectacular supernova. Therefore, a star with very low metallicity must have formed from that primordial soup before many stars had lived and died to pollute it. It's a simple yet powerful concept. The fewer heavy elements a star contains, the older it is. This hunt has been supercharged by our most powerful eyes in the sky. The Hubble Space Telescope gave us our first deep looks at infant galaxies in the distant universe, but its successor, the James Webb Space Telescope, is a true time machine. With its infrared vision, JWST can peer through cosmic dust and see the light from the very first stars and galaxies, stretched into longer, redder wavelengths by the expansion of the universe over billions of years. It's not just about seeing farther, it's about analyzing the chemical composition of these incredibly distant objects with stunning precision, allowing us to directly compare them to the ancient stars we've found right here in our own galactic backyard. And this isn't just an academic exercise. Every ancient star we find is a crucial data point that tests our grand cosmological models. The lambda-cold dark matter model, our leading theory of how the universe evolved, makes specific predictions about how and when the first structures formed. Did galaxies build up slowly from small pieces, or did some form startlingly fast? The properties of these ancient stellar systems tell us. They help us understand the nature of dark matter, the invisible scaffolding that guides the growth of galaxies. They even provide clues about the properties of the first generation of stars, the so-called population 3 stars, which have never been directly observed. They were likely behemoths, hundreds of times more massive than our Sun, living fast and dying young in violent explosions that set the stage for everything that followed. By studying the chemical legacy they left behind in these ancient survivors, we can begin to piece together their mysterious lives and deaths. This search for our cosmic ancestors is fundamentally a search for our own origins, connecting the elements that make us who we are today to the very first moments of time. So how do astronomers actually determine the age of a star? It's a complex puzzle that requires piecing together multiple clues, much like a detective building a case. The most fundamental clue is metallicity, the amount of elements heavier than hydrogen and helium that a star contains. Think of it like cosmic genealogy. The very first stars were born from the pristine gas left over from the Big Bang, which contained almost nothing but hydrogen and helium. When those massive first-generation stars ended their short lives in colossal supernova, they became the universe's first factories, forging heavy elements and scattering them into the cosmos. This means a star with extremely low metallicity must have formed from that unpolluted primordial gas, making it incredibly ancient. It's a direct descendant of the first stellar families. But astronomers don't stop there. They cross-reference this chemical fingerprint with other evidence. One powerful tool is the Hertzsprung-Russell diagram, which plots a star's brightness against its color. Stars follow predictable paths on this diagram as they age, so a star's position can reveal its stage in life. Ancient stars often fall within specific regions that point to their advanced age. Their motion through space provides another clue. Older stars tend to have more erratic, elliptical orbits around the galactic center, a relic from the chaotic early days of the galaxy's formation. They are the cosmic equivalent of seniors who remember the neighborhood before all the new development moved in. The science goes even deeper with a technique called Asteroseiology, the study of stellar vibrations. Just as geologists use earthquakes to probe Earth's interior, astronomers analyze the subtle flickers and pulsations in a star's brightness to understand its internal structure. The frequencies of these oscillations can reveal a star's mass, radius, and even its age with remarkable precision. It's like listening to the natural resonance of a star to hear its history. When identifying entire ancient star systems, the approach becomes broader. Researchers examine the collective properties of all the stars within a cluster or a dwarf galaxy. If the entire population shows a uniform, very low metallicity, it's a strong sign the system formed early and never experienced significant later star formation to enrich it with heavier elements. The spatial distribution of these stars also tells a story. Many of the most ancient systems are found in the galactic halo, a sparse, spherical cloud of stars surrounding the main disk of our Milky Way, which is a quieter, older neighborhood. This entire endeavor has been revolutionized in the modern era by data and artificial intelligence. Massive sky surveys like the Gaia mission are mapping the positions, movements, and properties of over 1 billion stars. The resulting dataset is so enormous that traditional analysis is impossible. This is where machine learning steps in. Algorithms are trained to sift through this ocean of data, identifying the rare candidates, those stars with the peculiar chemical compositions and orbital characteristics that mark them as potentially ancient. This allows astronomers to find these cosmic needles in a haystack with unprecedented efficiency. This multifaceted methodology is crucial. It ensures that the ancient systems we're about to explore aren't just statistical outliers. They are confirmed, well-studied relics that provide a clear and stunning window into the universe's infancy. Now let's meet our first ancient wonder, a star with a name that sounds like a serial code but holds a story more profound than any epic poem. SMSS J031300.36-670839.3. This star, found drifting in the vast halo of our Milky Way, isn't just old, it is the ultimate cosmic minimalist. Its composition is so pure, so untouched by the later chaos of the universe, that it holds the undisputed record for the lowest iron content ever measured in a star. To put that into perspective, it contains less than 1/10,000,000th of the iron found in our Sun. You have more iron in a single drop of your blood than exists in this entire colossal ball of plasma. This means this star formed from gas that was almost perfectly pristine, the primordial hydrogen and helium left over from the Big Bang itself. Based on this evidence, astronomers calculate it was born a mere 100 million years after the universe began. It is a true living fossil, a beacon that has been shining since the cosmic dawn, carrying within its light the chemical signature of a time before most of the elements we know and love even existed. But here's where the plot thickens and the star truly becomes a revolutionary. While it has almost no iron, it does show a surprising and significant enhancement of carbon. This is a crucial clue that completely upends our traditional thinking. It suggests this star did not form from completely virgin gas, but rather from a cloud that had been selectively polluted by the aftermath of a single, specific event, the death of one of the very first stars. This wasn't a standard supernova as we understand it today. The fact that it spread carbon without spreading much iron implies it was a different kind of explosion altogether. Perhaps a faint supernova or a hypernova that somehow ejected its outer layers rich in carbon while its core, where iron is forged, collapsed directly into a black hole, trapping those heavier elements forever. This single data point forces astrophysicists to completely rework their models of early nucleosynthesis, the processes that create new elements. It tells us the first stars didn't all die the same way. Some must have ended their lives in these unusual, asymmetrical explosions that selectively seeded the early universe with specific elements. This changes the entire chemical recipe for the subsequent generations of stars. Perhaps its most profound challenge is to the theory of star formation itself. The prevailing wisdom stated that the first stars, often called population 3 stars, had to be monsters, colossal giants hundreds of times more massive than our Sun. Their immense gravity was thought necessary to overcome the lack of metals, which act as cooling agents to help gas clouds collapse. These behemoths would have lived fast and died young in spectacular blasts, leaving no small survivors. Yet, here is SMSS J0313, a relatively low-mass star that has burned steadily for over 13 billion years. Its very existence is living proof that the early universe found a way to form smaller, longer-lived stars. Maybe molecular hydrogen provided enough cooling, or perhaps turbulence in the ancient gas clouds allowed for fragmentation. Whatever the reason, this star stands as a defiant challenge, proving that the cosmos's first chapters were far more diverse and inventive than we ever dreamed. While SMSS J0313 gave us a glimpse into the chemical signature of the first supernova, our next ancient star provides something even rarer, a cosmic birth certificate with a precise date stamped on it. Meet He1523-0901, a red giant star residing in the halo of our galaxy. What sets this star apart isn't just its age, but the incredible method used to determine it. This star acts as a natural radioactive clock. Deep within its atmosphere, astronomers have detected the presence of radioactive elements like uranium and thorium. These elements decay at a known, constant rate over billions of years. By measuring the current amounts of these radioactive isotopes and comparing them to their stable decay products, scientists can perform a technique called nuclear cosmochronology. It's like carbon dating, but on a cosmic scale. The result was astonishingly precise. This star is approximately 13.2 billion years old, making it one of the very oldest individual stars ever dated with such confidence. It was already an ancient red giant when our own sun was just a cloud of gas waiting to be born. But the real shock from this stellar senior wasn't just its age, it was its sophisticated chemical makeup. Within its spectrum, astronomers found the clear signature of what's known as the rapid neutron capture process, or the R process. This is the extraordinary series of nuclear reactions responsible for creating about half of all the heaviest elements in the universe, including gold, platinum, and the very uranium used to date it. The prevailing theory stated that the R process required incredibly violent and rare events that simply shouldn't have been happening so early in the universe's history. We thought it needed the cataclysmic merger of two neutron stars, or perhaps a very specific, rare type of supernova events that were believed to require multiple generations of stars living and dying to set the stage. The existence of these elements in He1523 means that somehow, in the cosmic blink of an eye after the Big Bang, these incredibly powerful events were already taking place. The early universe, which we often picture as a simple, quiet place with only hydrogen and helium and the first few generations of stars, was apparently a much more dynamic and explosive environment than we ever imagined. It suggests that neutron star mergers, these incredible cosmic collisions that shake the fabric of space-time, were happening far sooner than our models predicted. This completely rewrites the timeline for the production of heavy elements. It means the universe was seeding itself with the building blocks for planets and life much earlier than we thought possible. The chemical diversity of the cosmos didn't build up slowly over eons. It might have gotten a surprisingly fast and furious start, challenging our fundamental understanding of how quickly the universe evolved from a primordial soup into a complex chemical laboratory. Just when we thought we had the early universe figured out, along comes a star that defies every expectation so completely that astronomers literally called it the impossible star. SDSS J013915+172927 is not just old, it's a paradox. This so-called population 2 star has a metallicity so incredibly low that it pushes up against the absolute theoretical limit for star formation. According to our best models, a gas cloud this pristine should never have been able to collapse and fragment to form a small, long-lived star like this one. It simply shouldn't exist, and yet there it is, shining in our data as a glaring exception to the rules we thought were fundamental. To understand why this star is so baffling, we need to look at the basic physics of how a star is born. It starts with a vast, cold cloud of gas beginning to contract under its own gravity. As it collapses, the gas heats up, and this increasing internal pressure fights back against the gravitational squeeze. For the cloud to continue collapsing and break up into smaller, star-sized fragments, it needs a way to release that heat to cool down. In the modern universe, this crucial cooling is done by heavy elements metals in the form of microscopic dust grains. These tiny particles radiate thermal energy away very efficiently, allowing the dense cores within the cloud to lose heat, overcome the pressure, and finally ignite into stars. But the gas cloud that formed SDSS J031300 had virtually none of these metals. It was almost purely hydrogen and helium. According to every simulation, such a cloud wouldn't be able to cool effectively. It would stay too hot, preventing it from fragmenting into small clumps. Instead, the entire massive cloud would likely collapse into a single, enormous behemoth of a star, a short-lived giant hundreds of times more massive than our Sun, that would die in a spectacular supernova after only a few million years. The fact that this star is a low-mass survivor means our understanding of the early universe's star-forming mechanics is fundamentally incomplete. So how did the impossible star form? Its very existence forces astronomers to propose new and exotic physics for the cosmic dawn. One leading theory points to molecular hydrogen. In the absence of metals, molecular hydrogen, or H2, might have served as a potent cooling agent in those primordial clouds. When hydrogen molecules collide and rotate, they can emit infrared radiation carrying energy away. Perhaps under just the right conditions of density and temperature, this mechanism was efficient enough to allow for fragmentation, creating a few rare low-mass stars among the predicted giants. Another, more recent idea suggests that even in the very early universe, there might have been a tiny amount of dust. Not dust from previous stars, but perhaps dust formed in the exotic outflows of the very first supernova, or in the atmospheres of the universe's first red giant stars. Even a minuscule amount of this primordial dust could have provided the necessary cooling boost to tip the scales and allow a small star to form. The discovery of this single star has opened up entirely new branches of theoretical astrophysics, with researchers now running complex simulations to see if these alternative cooling pathways are indeed viable. This makes SDSS J031300 more than just an astronomical curiosity. It is a critical key to understanding the initial mass function of the first stars. Did the early universe only create monstrously large stars, or was there a diverse population that included smaller, sun-like stars that could potentially host planets and burn for billions of years? This star strongly suggests the latter, meaning there could be many more of these ancient, low-mass survivors hiding in the galactic halo, quietly burning away as living relics from a time when the rules of creation were being written. It challenges us to rethink one of the most basic processes in all of cosmology, reminding us that the universe has always been far more inventive and surprising than our models can predict. Moving from individual stars to entire systems, we encounter one of the most bizarre and pristine relics in our cosmic neighborhood, the Segue 1 dwarf galaxy. This isn't a grand, spiral spectacle. It's a faint, ghostly smudge of light orbiting the Milky Way, so dim that for decades it was lost in the glow of its massive host. Within this unassuming collection of just a few hundred stars lies a profound mystery. Every single star in Segue 1 is ancient, with metallicities so low they rival the most primordial stars we've found anywhere. The entire galaxy is a time capsule, a snapshot of what the universe looked like mere hundreds of millions of years after the Big Bang, preserved in a state of suspended animation. The most baffling aspect of Segue 1 isn't just the age of its stars, but its complete and utter lack of chemical evolution. Think of a typical galaxy as a bustling city. Stars are born, they live, they die in supernova, and those explosions enrich the surrounding gas with new, heavier elements. The next generation of stars then forms from this richer material, building up complexity over time. Segue 1 is a city that had a single, brief industry that shut down on its very first day. It experienced one initial burst of star formation, and then, for reasons we don't fully understand, it simply stopped. The supernova from that first generation should have polluted the galaxy with enough heavy elements to kickstart a second wave of star birth, but it never happened. The gas was either blown away entirely by those first explosions, or it was somehow prevented from collapsing again. This challenges all our models of galactic evolution, which predict that even the tiniest galaxies should have at least a few cycles of star formation. Segue 1 defies this completely, presenting itself as a fossilized embryo of a galaxy that never grew up. This strange history makes it an unparalleled laboratory for studying the most elusive substance in the cosmos, dark matter. Measurements of the star's motions reveal something astounding. The total mass of this tiny galaxy is hundreds of times greater than the combined mass of all its visible stars. The overwhelming majority of Segue 1 is made of dark matter, giving it one of the highest dark matter to normal matter ratios ever observed. This is a crucial clue. It suggests that the very first structures to form in the universe weren't stars or galaxies as we see them today, but rather clumps of dark matter known as halos. These invisible gravitational wells acted as seeds, gathering the primordial hydrogen and helium gas needed to form the first stars. Segue 1 appears to be one of these pristine dark matter halos that managed to form a handful of stars and then, for some reason, shut down, preserving the original, intimate relationship between the dark matter and the visible universe in its most basic form. It allows us to study the properties of dark matter not in some abstract way, but through its direct gravitational influence on these ancient stars, offering hints that it might be colder or less interactive than some theories have proposed. Ultimately, Segue 1 is more than just an ancient system. It's a cosmic archaeological site that has remained untouched for billions of years. Its existence tells us that the early universe was littered with these failed galactic experiments, tiny pockets of star formation that flickered on and then off again forever. Most were likely torn apart and absorbed by larger galaxies like our own, their stars scattered into the halo. Segue 1 is a rare survivor, a fragile relic that has somehow endured next to a galactic giant, offering us a direct look at the modest, stumbling beginnings of galaxy formation and challenging our assumptions about how even the smallest structures in our universe live and die. We've been exploring ancient stars tucked away in the quiet halo of our galaxy and faint, distant dwarf systems, but now we turn our gaze to the most dramatic and crowded place in the Milky Way, the galactic center. This bustling, dense region, known as the Bulge, was long thought to be a product of the galaxy's later, more violent history, forged through colossal mergers and the slow, steady churn of stellar evolution. It's a place of immense gravitational forces shrouded in dust and home to a supermassive black hole. The conventional wisdom was clear. The Bulge is a dynamic, evolving structure, a melting pot of stars from various eras and origins. That's why a series of recent discoveries has sent such a profound shockwave through the world of astronomy. Hidden within this modern cosmic metropolis are stars that are astonishingly ancient, with ages exceeding 13 billion years. Their presence there is not just surprising, it forces a complete rewrite of our galaxy's origin story. Finding these stellar seniors in the Bulge was like discovering a prehistoric cave painting in the basement of a modern skyscraper. It defies all expectation. The primary method for uncovering them was once again chemical detective work. Large spectroscopic surveys meticulously analyzed the light from thousands of bulge stars, searching for those with the telltale sign of extreme age, incredibly low metallicity. To the astonishment of researchers, they found them. These ancient bulge stars possess a chemical fingerprint identical to the oldest stars found in the halo. They are made from nearly pure primordial gas. But their location is what makes them revolutionary. They aren't just visiting, their orbits are confined to the bulge, indicating they were born right there in the galactic center when the universe was in its infancy. This discovery shatters the previous leading theory of bulge formation, which argued it was built over time through a process called secular evolution. This model suggested the bulge grew from the inside out, with the central bar of the galaxy funneling stars inward from the disk over billions of years. Others proposed it was assembled primarily through dramatic mergers with smaller galaxies later in cosmic history. But the existence of a native population of ancient stars changes everything. It means the core of our Milky Way is not a later addition. It is a primordial foundation. It formed with breathtaking speed in a ferocious burst of star formation that may have lasted less than 1 billion years after the Big Bang. This rapid collapse model suggests a vast cloud of primordial gas collapsed directly under its own gravity, triggering a starburst of epic proportions that built the galaxy's dense core in one frantic, glorious rush. This isn't just a minor adjustment to our galactic timeline. It's a fundamental shift in perspective. It positions the Milky Way as a disk galaxy in a new light, suggesting its very heart is one of the oldest structures in the entire universe, a relic that has witnessed the entirety of cosmic history. It also provides a fascinating solution to a long-standing puzzle in cosmology, the formation of supermassive black holes. Our galaxy's central black hole, Sagittarius, a star with a mass of 4 million suns, now appears to have grown in tandem with this ancient bulge. The rapid collapse of that initial giant gas cloud would have provided the perfect conditions to feed a nascent black hole, allowing it to grow to a colossal size very early on. The ancient bulge and its central black hole are not separate entities. They are part of the same primordial event, a foundational act of creation that set the stage for everything that followed. The implications ripple far beyond our own galaxy. If the Milky Way's bulge is this ancient, it challenges our understanding of how all large galaxies assemble. It suggests that the central bulges of many galaxies might not be the products of later chaos, but could instead be their oldest, most stable cores, the seeds around which the rest of the galaxy slowly accumulated. This turns the standard model of hierarchical galaxy formation on its head for some systems. Instead of growing from the bottom up through mergers, the Milky Way may have formed from the inside out, with its ancient heart beating first and its majestic spiral arms growing slowly around it over eons. This one discovery from the crowded center of our own home galaxy forces us to reconsider the very sequence of events that built the cosmic structures we see today, proving that even the most familiar parts of the sky can hold the deepest and most surprising secrets. Leaving the bustling center of our galaxy, we now venture to one of its most remote and fragile frontiers, a place where the very nature of cosmic survival is being tested. Drifting through the vast, dark halo of the Milky Way is the Hercules ultra-faint dwarf galaxy, a system so ghostly and sparse that it barely qualifies as a galaxy at all. It is a wisp of starlight, a collection of only a few thousand stars held together by its own gravity and a massive halo of dark matter. What makes Hercules so extraordinary isn't its size, but its incredible purity. The stars within it are among the most chemically primitive ever discovered, with metal content so low they are almost immeasurable. This tells us that Hercules formed from gas that was almost perfectly pristine, a direct remnant of the Big Bang itself. It is a surviving pocket of the primordial universe, a place where time seems to have stood still for over 13 billion years, preserving a moment just after the first stars began to shine. This ancient character is written in the very motion of its stars. Observations reveal that Hercules is not a neat, spherical cluster. Instead, its stars are stretched into a long, thin stream, arcing across space like a faint celestial ribbon. This dramatic shape is a telltale sign of a violent gravitational interaction. The immense tidal forces of our Milky Way are actively pulling this tiny galaxy apart, stretching it from both ends in a process known as tidal disruption. It is a cosmic tug-of-war that Hercules is inevitably losing, slowly being digested by its colossal host. This ongoing destruction provides astronomers with a rare and valuable opportunity. They can literally watch the physics of galaxy assimilation happening in real time, studying how the gravitational pull of a large galaxy strips away stars and dark matter from a smaller companion. It's a front-row seat to the process of galactic cannibalism that has built large galaxies like our own over billions of years. Yet, here lies the profound paradox that makes Hercules such a challenging puzzle. Despite being caught in the gravitational grip of the Milky Way and being torn apart, the stars within Hercules show no signs of chemical pollution. They remain pristine. This is completely counterintuitive. As a dwarf galaxy orbits a large one, it should pass through the vast, hot halo of gas that surrounds the larger galaxy. This gas, enriched by countless supernovae over eons, should slowly sweep through the dwarf galaxy, polluting its own interstellar medium and leaving a mark on any new stars that might form. The fact that Hercules' stars are so pure means it has never experienced this pollution. It has either managed to avoid plowing through these enriched gas clouds entirely, or its own gas was stripped away so early in its history that there was never any opportunity for a second generation of polluted stars to form. Its survival in this virginal state, right under the nose of a giant galaxy, forces a major revision of our models about how these interactions work. It suggests that ultra-faint dwarfs can be incredibly resilient time capsules, protecting their ancient contents even as their structures are violently dismantled. This resilience makes the Hercules dwarf an unparalleled local laboratory. While telescopes like JWST are peering back in time to see the first galaxies at the edge of the observable universe, Hercules offers us a way to study the physical conditions of that early epoch right here in our own backyard. Its stars are nearby enough that we can analyze their light in exquisite detail, measuring the precise abundances of elements that were forged in the very first supernova. It gives us a ground truth check for the observations we make of incredibly distant young galaxies. Furthermore, its incredibly high dark matter content provides a unique window into the nature of this mysterious substance. By mapping the motions of its stars as they are pulled away, astronomers can create a detailed picture of how the dark matter halo around Hercules is itself being distorted and stripped, offering crucial clues about whether dark matter particles are cold, warm, or if they can interact with each other in ways we haven't yet imagined. Ultimately, the story of the Hercules ultra-faint dwarf galaxy is a story about fragility and endurance. It is a relic that has survived against astronomical odds, preserving a record of the universe's infancy through eons of cosmic violence. Its continued existence challenges the idea that all small galaxies are quickly and efficiently assimilated and polluted by their larger neighbors. Some, it seems, can retain their ancient identity even in the process of their own destruction, giving us a precious and direct link to the time when the first structures were struggling to form out of the dark, silent cosmos.